this is 14, 15 equal to. I don't answer. Yeah. There is only one function. I have said, prove this in my notes. I did not give you notes, so you don't need it. Finally, if you want, you can take copies, but no need. What he says is that note that for each set x, there is only one function from empty set to x. If you take x, you have to have domain and range. There is only one function from empty set. No, that's what it says. So. Note that for each set, there is only one function from 5 to x. Suppose f1 and f2 are two functions. Suppose f1 and f2 are two functions. From FROI, from empty set to x. We need to show that they are equal. How do we show? Same domain, that part is correct. Domain is empty set. Now we have to show that for each x belongs to empty set, f1 of x and f2 x are equal. But there is nothing to say. So it is kind of nothing to write. We have to say the same. No? For each x belongs to empty set, we cannot write like that. So empty set is function itself is in our mind. Cannot write on the board. Since there is no x belongs to empty set, f1 must be equal to f2 because domain of phi 1 is equal to domain of empty set 1 f1. Sorry, is equal to domain of f2. So it's kind of nothing to write, but we should agree that for that. Again, he is saying, since definition 3.3.7 asserts that all functions from 5 to x are equal. Again, the same thing. So they are kind of the theoretical things, not in analysis. These are important. Sometimes you have to know some topology to be an analyst. Then this kind of things come set theory to you. You are going to compare with that stuff. So very important. Next one is composition. That's a very important one. Composition. Yeah, what's a better one? I don't know really. Composition of functions. Composition is like this. You have one set here, you have another set here, you have another set here. Say, let's call it this guy is X, this guy is Y, this guy is Z. In USA, because you are, all three are planning to go to USA, they call it Z, not Z. In Sri Lanka, we call it Z. So I sometimes say Z because I'm in Sri Lanka. And sometimes it comes from my mouth, it is Z. Some people wonder, what is Z? So Americans are, they are funny people. This is, they call this one Chicago. However, this one, not chicken, but after after the first time I was in USA, during the first break I went to Chicago. When I came back, I had a friend from Chile. Chileans are like us. They are, of course, like you, skin color wise. Manners wise, they are like us, not like Americans. So we were very good friends. He asked me, Rama, where did you go for the break? I said, I went to Chicago. Where did you go? I said, I went to Chicago. Where? I said, Chicago. Where on earth? So can you write it down on a piece of paper? Then he gave me a piece of paper and a pen. I wrote this one. Ah, Chicago. Then I asked him, hey, how why do you say this one? Chicken instead of chicken. He told me that's the way US is. Anyway, so, wait, you have now one function here, you have function here, x to y, you have the function f. And y to z, you have the function g. This is like, if you go to a factory where glasses are made, to any factory, you put the things, input from here, it goes to this machine, and it goes to another machine, it goes to another machine, like that. Now, final thing comes from after many machines. Like that here, you get x, from here it goes to fx. Now, where is f? I need to write that. G. Now, G acts on fx and produces g of fx. G of fx. So if you take x suddenly go to, you take x goes to this one, we call it G circle F. This is how we write G circle F. G circle F of x, by definition, is G of fx. Now, something important here. Just because of x goes to fx, now fx must be in the domain of G. Otherwise, this doesn't work. This does not work. Suppose by any chance you have one function from say r to 0, 1, then the other function is 10 to 10 to, not 10, 22. This is f. This is g. Say r again. You cannot talk about f circle g. Why? The values of fx are in the interval 0, 1, not here. So there is no composition. That's why here the definition is written composition. Here he says, let fx to y, g by to z be two functions such that the range of f is the same set as the domain of g. Though he writes like this, it can be that range of f is contained in domain of g. It can be, say, it is possible that range of f is like this one, this is range of f, and domain of g can be a bigger set. Still, this works, no? From where? Here. It's the same that domain of f. We then define the composition g circle f x to z of the two functions g and f to be the function defined explicitly by the formula g circle f of f is. He wrote this. I don't know the English word for this symbol. Anyway, double dot equal, let's say. Is g of fx. Thing is that when you, though here you have g first, here you have f first. That's how it works. So at the beginning you can get a little confused. Here, over there, we call g circle fx. But when you draw a picture, f comes first. But here also f acts first on x. So don't get confused. I mean, these are little things. If the range of f does not match the domain G, we leave the composition G circle F undefined. So that's again incorrect somewhat because they don't match. Here still you can define. In many examples you get an analysis are like this. Range of f is a subset of domain of G. So you can define the composition of functions. Almost 99% of the examples you get in analysis are like this. You have to get composition quite often. Definition. So that statement again is not good. No? You don't have to have the same range of f doesn't have to be equal to the domain of G. As long as range of f, you follow this. You have to follow something in order to come to lunch. If the range of f does not match the domain of G, we leave the compression G circle F undefined. So if we are writing, we have to say if the range of f is not contained in the domain of f G, then they are not undefined. But we don't have to, correct what we write as long as we understand the thing. Here's an example. Let's see. Did I jump? No. Let f n to n be the function fn equals to n, he is writing. G n to n be the function gn equals n plus 3. Then G circle f is the function. Here, because it's kind of one can misunderstand. Here, what is happening here? First set, this one is n, this one is also n, this one is also n. Just because you have f n to n and g n to n, then at once little bit confusing because this is the picture of when you can take the composition here. Somehow it happens to be that all the sets are equal to n, all of them are n. G is Fn is 2n. Here f n goes to 2n. You begin from n, it goes to 2n. Here is g, but g does is g of any n is n plus 3, then g of 2n is 2n plus 3. Is that how we have 2n plus 3? So that's how you take. Because it's very important this one, because you get compression when it comes to analysis, continuous, differentiable, everywhere. This is all over. And so forth. He says G circle f of 1 you can compute. That goes without saying f of 2 is 7 and so forth. Meanwhile, f circle G, here when you have the same function, now I can put here G. Now, if you take G n, then this G of n is, I suppose, 2n plus 3. No? G of n is n plus 3. Then G of under f, this goes to twice n plus 3. So 2n plus 6. Right? 2n plus 6. So here f circle G circle f of n is 2n plus 3. No, 2n plus 6, no? Our f circle G of n is.
First one is 2n plus 3. G of
2n plus 3, no? This one is 2n plus 6. So both of them, f circle G and G circle f are not the same. That's the important thing. So you should not get confused that because to many students it is a problem. You write first here F, but you write G second F. Anyway, then this example, composition is associated. Or proof is in the book. I don't know whether it is a very simple proof. Let's anyway prove it. Shall I go? Okay. The proof is here. Yeah, I don't have to write.
Yeah,
everything. Now, if I have this picture, we are talking about F circle, G circle, H. So let me erase this. When you are reading the book, don't take anything for granted. That's the way to learn mathematics. If you can fill the details of whatever you read, then you will learn mathematics. F is talking about F circle, G circle, H. You have here H. H goes X, Y, Z, and W, Y, no G, Y, Z. This guy goes to W. It is H. So here you take X, it goes to Fx under F, under G, Fx goes to D of Fx, under H, it goes to H of G of Fx. H of G of Hx, it goes to that. So now, however, you can see from for the new thing. X and F goes to Fx and G, Fx goes to G of Fx, and H it goes over there. Then here H is, am I right or wrong? H of F goes from
First H should come first, right?
yes, written.
First
I
H.
have a different thing. F is from Z to W, no?
Yeah.
So let's draw a new picture according to him. All these are algebraic things. Algebra and analysis is very different, but linear algebra is very important for analysis. You are doing some linear algebra. So according to here, you have Z to W. F goes from Z to W. G goes from Y to Z. And H goes from X to Y. So then we have to show that you have, we said, if we want to show a circle, the circle H is equal to F circle G, circle H. So what is happening is you have one set here, another set here, another set here, another set here. This is atlas. Yes. So then this must be H, no? Then it must be G. It plus with F. So H goes from Z to W. This is Z. This is W. This is E goes from Y to B. What am I doing? F goes from Z to W.
Plus H plus X goes to Y. X goes from
Then Y goes to
Yeah.
Z.
Is this correct? I have it.
on the left hand. You should
I think you start from H.
you should start from X. The set
This one is X.
Yeah, then Y.
Next one is
Y
Y. This one is
Z.
oh, natural numbers is a triangle. This is then this function H is correct, no?
Yeah.
X to Y, then G goes from Y to Z, and F goes from Z to W. So if you take from here to here, X, Y, Z, W, this function is G circle H. This function. Then from X to Z you have G circle H. Then from here to here you have F. Therefore, from here, now this is F. Already you have it. Then if you take the composition, then you get F circle G circle H. On the other hand, if you can pursue compression from here to here, you take F circle G.
G.
Yeah, no?
Yeah.
F circle G, that's correct. Then from here to here you get H. So then when you combine these two, you get F circle G, circle H. So in two different ways we combine, take the compression, we have to see that they are equal. Since G circle H is a function from X to Z, F circle G circle H is a function from X to W. Similarly, F circle G is a function from Y to W, and hence F circle G circle H is a function from X to W. He is just saying that domains and ranges are both same for both the functions. After that, it is nothing actually. That F circle G circle H and F circle G circle H have the same domain and range. In order to check that they are equal, we see from definition that we have to verify F circle G circle H of X is equal to F circle G circle H of X for all X in X. So if you are writing the proof, don't write like this. You have to write the statement, let X belongs to X. Then you write like this. Nobody knows where on earth X come from. Because in order to learn analysis, you have to have all the details. So that's not good. Somehow, anyway, he has taken some X in X. Then F circle G circle H of X. By definition, what it means? F of G circle H of X. F, this parenthesis, F of G circle H of X. That is correct. Then he is simplifying that. F of G circle H of X is F of part remains the same. G circle H of X is G of Hx. So you get now F of G of H of X. However, now you can say this one is F circle G. Because you have the element here Hx, you are assuming this is your element, the F of G of some element. So by definition it is F circle G of this element. Now you think this is a function, this is another function, therefore F circle G, circle H of X. So it's not anything big, but it's very important to know it. Then afterward, note that, this note, it's not important for you right now, but I told you that here interchange the first one here, though this is the leftmost function, here it is the rightmost. It goes in a different order, how we write. But then what he is saying here is this paragraph, let's not read it, it's not important for you. For analysis it's not important. But this doesn't work, my fingers.
Use both fingers.
Eh?
Use both fingers at once. No, get the cursor down first.
Well, no, something else.
Keep the cursor in the middle as we have, not just use both fingers.
Anyway, what he says, let's just read it then. Note that while G appears to be on the left of F in the expression G circle F, G appears to the left of F. The function G circle F applies the rightmost function F. That's the base guy. Because this guy F acts first, that's what it says. Then G acts later. Before applying G, this is often confusing. At first, I told you, it arises because we traditionally place a function F to the left of its input X rather than to the right. There are some alternate mathematical notations in which the function is placed to the right of the input. Some people write, instead of writing Fx, very rare, some differential geometry equations books I have seen this way. There is a reason for them over there, but you don't get that in an analysis course. It is always f of x, not xf. But you need to remember that there are some people, some places, but this notation has often proven to be confusing. Actually, I was doing that last year with somebody. To me, very confusing. But I am used to f of x, then you say xf. It is funny. Be more confusing than clarifying, and has not yet become particularly popular. Now we describe certain special type of functions, one-to-one functions and on-to functions, and invertible functions is very important. You have heard this one? Again, let's see how he writes the definition. Now I have learned how to use this also. No? This time it is going good. Yeah, okay. He says one-to-one functions. The function f is one-to-one. Some people write one-to-one this way also, by the way, when they are lazy. One-to-one. Right, like this. One-to-one functions. The function f is one-to-one but injective. When I came to campus, I came from village. My teacher was saying about injection. I got nervous injected something. So anyways, the word it has injection. If function is an injective, it is called an injection. Yeah, anyway, a function f is one-to-one if different elements map to different elements. Again, it is not written in real logical way. How? Because you have a function f. We have. Maybe I should buy a plane next day, or else we should ask him to buy it. Here, this one is. Does this work? Yes. Maybe not very long it will work. Because so much of incomes. You have a function f from x to y. X to y. Then such a function is said to be one-to-one. So a function f from x to y is called or is said to be whatever. Said to be 1 to 1, 1 to 1. According to him, he writes, this time he is if, not if and only if. 1 to 1, if, not if and only if. I don't know. That's why I think this book was written by some Indians, and they put that. In Sri Lanka also it happens, no? So some people in Sri Lankan parliament, they get PhDs. Somebody else has written the thesis. So it could be like that, said to be 1 to 1. If anyway, I'm happy that at least once I do. Now I tried all these things. No? This one, then it will be difficult to erase the book. If, how do we write? For each, we have to go and find. So we are going to write the definition of 1 to 1, no? The function f x to y is said to be 1 to 1 if for each, according to him, x dash belongs to x equals x, he is writing x is not equal to x dash, implies fx is not equal to fx dash. No matter which pair of x and x dash you choose from x, if by any chance x is not equal to x dash, then fx is not equal to f dash. You can write the, now f is not 1 to 1, you can write the definition right away. You need to start doing that. Then you will become logical and ready to learn maths right away. Thus, if x to y is not 1 to 1, what should it should be? Not 1 to 1.
For some x, x dash belongs to x.
Shall I write there exists?
Yeah.
I like that style. There exists x dash belongs to x. Then next two words. Here, for the good. There exists two of them. X dash belongs to x.
X equals x dash.
No.
X not equals x dash implies.
Such that you need to such that
X equals x dash.
x
Equals x dash
equals x dash
implies
implies
fx equals fx dash.
incorrect. No lunch. Kuda, what should I write? There it is x dash belongs to x such that
X is not equals to x dash and fx equal to fx dash.
so if you draw a picture, this is very clear. Very clear. You have x here, you have y here. 1 to 1 means if you take it now here, not 1 is easier to understand. X dash here, they are different, but they go to the same thing. So actually this is not 1 to 1, it is like 2 to 1. Two of them goes to 1. So always try to work this way. I mean, even though he writes like this, and of course, same thing can be written this way, fx equals ff dash implies x equals x dash. Equivalent, let me write that also here. Equivalent. equivalently. For each x dash belongs to x, fx equals fx dash implies x is equal to x dash. If two images are same, then their three images are also the same. That's what it means. Right? Now, something you need to learn here. Said to be one-to-one if by appearance you have written in two different ways. By appearance, but they mean the same thing. Here, if you write this one, negation of this, if you are using this definition to write f(x to y) is not one-to-one, what will you get? There it is x dash belongs to x, such that fx equals fx dash and x equals x dash. You get the same line. That's what I wanted to say. Here they look different, but when you are going to write not one-to-one definition, it doesn't matter what you use, you end up with the same thing. That's it. Okay, so anyway, that's the meaning of one-to-one. So, what one-to-one means. Now, for a function, some people misunderstand. So, if you take a function, when you take one x, there is exactly one fx here. Given any x, there is one fx. But here, this one is very different. If you take any x dash, if they are different, their images are also different. That's what it says. So very important one. One-to-one in algebra analysis everywhere. One-to-one functions are important. Where am I? Yeah, really. Here he says, you have this example, let me see whether I'm learning how to use this. What?
Move the cursor away from one thing and do the two-finger thing again.
So it's
So just click, yeah, just click somewhere.
Okay.
Now, scroll.
Now come.
Yeah.
I have a laptop at home. I did use it once in the room. Anyway, so here he is talking about z to z defined by fn equals n square. N square is not one-to-one. Why? Because you have 2 and minus 2. They are different, but their images are the same. So not one-to-one. However, if you make the domain to be just n, then gn equals n squared is one-to-one. Remark, the function f x to y is not one-to-one, then one can find distinct x and x dash in the domain such that fx equals fx dash. So that's what we have written. So he is not writing this in a very logical manner. That's the thing I'm not that happy. Thus, one can find two inputs which are to one output. Because of this, we say that f is 2 to 1 instead of 1 to 1. I mean, you cannot, that is again incorrect. If you want to say 2 to 1, it should be if you take, always you have to have two things go to, here once in a way it goes to 2 to 1. Can you see what I'm saying? 1 to 1 is always, if you take distinct three images, you have distinct images. 2 to 1, yeah, you have to have two things going to 1 quite often, not once in a way. Anyway, it is not that interesting. Then we.
So if the inverse of the function is at minus 0,
it could have been a 2-to-1 function.
I'm sorry, G n to n z.
F z goes to z function.
Yeah.
Fn equals n squared.
Yeah.
So if the domain was in z minus 0, it is a 2-to-1 function. No?
Exactly. But to us, 2-to-1 functions are not important. I mean, it's just bringing the word. Because 1-to-1, somebody can ask, and there are functions 2-to-1 in complex analysis, many to 1. Yeah. Okay, now definition onto functions. That is again very important. The function f is onto. Oh, by the way, 1-to-1 functions are all injective. 1-to-1 function is an injection. Injective. Onto functions, a function f is onto or surjective if fx equals y. That is, every element in y comes from applying f to some element in x. For every y in y, there is x in x such that fx equals y, written exceptionally well. That's the meaning of onto functions. The function f is from x to y is said to be onto if for every y in y, there is x in x such that fx equals y. Then what is the meaning of f is not onto? Function going from x to y. What is it? The function f x to y is not onto. Even though we are taking time, doesn't matter because we have learned it at the beginning this well, then we can accelerate. Sooner or later we will be going very fast like who are going to matter. Sooner or later it will happen. Is not onto if what? Puta, who is interested in the lunch at Mount Lebanon? මොකද පුතාව? A function f x to y is not onto if what? Here, a function f is onto or surjective if for every y in y, there is x in x such that fx equals y. Then it is not onto.
Some.
Okay, for some.
Some y from every element of y.
පුතාව
For some, if there exists y,
there exists y, there exists y in y such that, very good. Practice the habit of saying there is, as soon as you write there exists such that. So, gradually you will become mathematical. Yes, such that.
for all x.
Very good. For all or for each or for every, for all x in x, comma,
Fx is not equal to
fx is not equal to. Very good. You are starting from for some, that is, you can write also that if for all x in x, fx not equal to y, for some y in y. Quite often, if you are writing for some, that is better to have at the end. I mean, it's not a rule, but you feel at home with having for some at the end. So, but there is better because it gives mathematical. For some is an English word. It exists also an English word, but this exists. People don't use no in when you are talking in English. Dialects you don't use that much because it is highly logical here in maths. Okay, so example 3.3.88, f is defined by fn is equal to n square. It's not onto because the negative numbers are not in the image. Try to be logical because we are going slow now. After this chapter also I want to accelerate even though I am now going slow. After 2 more chapters, so we are like Guru Kumari going to matter. But you have to have the foundation at first. Buddha, now, here he says informal, the function f is defined by fn equals n square is not onto. So suppose this is one. F n to n, let f n to n be defined by fn equals n square. So in my case, I write f for all n actually. He is not writing like that. Because f doesn't have to have the same formula. It can have many formulas. That's what analysis is about. So that's why I always write for all n here. But he doesn't write. For the time being, it is okay whether you write it or not, but sooner or later, some functions it can be f of n is equal to n squared if n is even, 3n plus 1 if n is odd. 2 different ways of defining. Right? So that's anyway, it is redundant for us for the time being. Now, at you show that. Little proofs you need to practice writing. Show that f is not onto. Put that, you proof. Proof. I want to prove that fn equals n square is not on. Proof is here on the board from the book. But I want to write in the way that a student writes a proof. That's why I'm asking you. According to this definition, what? First we have to choose some y in y such that no x matches to y. So give me such a y. Clearly, let's say, clearly, what number is not matched by this f? There are many numbers, give me one of them. 2? That's not so good. 2 is not matched. Very good. Clearly 2 belongs to n. 2 belongs to n. What is that? Oh, observe that something, whatever you like. I guess you guys have everything is that I do. What is that? For each n belongs to n, n squared is not equal to 2. You took, here you have n means are provided by the institute, you see. Here in this case, both main and range are the same. You took 2 from here. Then you are saying no matter which n you take from here, n squared is not equal to 2. Thus, f is not 1. That is the proof. Though it is very simple, we learn how to write. You need to practice writing little short proofs. Then what we see? Solve the conflict. So, one-to-one functions are called injections, one-to functions are called surjections. If you have injectiveness and surjectiveness both, we call it bijective. Bijective. Bijection. The function f x to y, which are both one-to-one and one-to are also called bijective or invertible. Bijective means both injective and surjective, both one-to-one and one-to. Bi means two, no? Binary two. By law two. That's incorrect. By law is something. It has its own meaning. You have to be careful learning English from me. So bijections are very important, especially in algebra. Groups, rings, fields, always bijections. Bijections. They have a different word for that. Isomorphism. Yeah. Okay, anyway, now let's go to the example also real quickly. f0, 1, 2, 3, 4 is the function, f0 equals 3, f1 equals 3, f2 equals 4. This function is not Barkheim because if we set y equals 3, then there is more than one x in 0, 1, 2. Because f of 0 and f of 1 both are equal to 3, therefore f is not 1 to 1, therefore f is not bijective. More than fx equal y square. Now let g goes from 0, 1 to 2, 3, 4 is the function. G0 is 2, G1 is equal to 3. Then G is not bijective because if we set y equals 4, then there is no x for which Gx equals y, right? That's clear. To you, is it clear, Bhutai? Though they say clear, you don't have to agree with them. If it is not clear to you, you should ask. That's why you are here. Because if you don't understand today, but sooner or later you will beat them, both of them. Now let h going from 0, 1, 2 to 3, 4, 5 be the function f0 is 3, f1 is 4, h2 is 5. Then h is bijective because each of the elements 3, 4, 5 comes from exactly one element from 0, 1, 2. Exactly one element. That is injection. 3, 4, 5 is everything in the range. That is, it is on both 1 to 1 and on 2. Let's see now whether it will do. Oh, it's working now. I may become an expert in computing, no? Computer. Okay, a function f defined by fn equals n plus plus is a bijection. It is of course no n plus plus, no he writes n plus 1, this is n plus 1, no. It is of course 1 to 1, on to because 0 is not in the domain, sorry, range. On the other hand, the function g n to n defined by the same function is not a bijection because it is not onto. If you make the range second one n to n, then it is not onto. Oh, you can see, I'm reading you, no? Remark 3.3.24. Oh. I guess I got. This paragraph clear, Buddha? To you is it clear? I can, to you is it clear? One function is going from, on the top, n plus plus. If you are going from n to n minus single than 0, n plus plus is actually n plus 1. It is definitely 1 to 1. It is not onto because 0 is not in the range. But if you make 0 to be in the range, then it will not be 1 to 1. There is no integer n such that n plus plus is equal to 0. We studied that. So, if a function x to fx is bijective, then we sometimes call f a perfect matching or a one-to-one correspondence. That is very important for us. The second, one-to-one correspondence set of words. If it is bijective, we call it a one-to-one correspondence. Not to be confused with the notion of one-to-one function. One-to-one function is and one-to-one correspondence are completely different. Because one-to-one correspondence is one-to-one and on-to both. One-to-one correspondence. One-to-one is just one-to-one. We discussed it. And denote the action of using, we write like this way also. X corresponds to fx instead of here x goes to fx, x is matching to fx here, x and fx are corresponding to each other. Thus, for instance, the function h in the above example, h is one-to-one correspondence. 0 to 3 we write like this. How they are matched. 0 is matched with 3, 1 is with 4, 2 is matched with 5. That's important. Then next one is talking about common error. Let's not read it. Common error part I am not reading. If f is bijective, then for every y in y, there is exactly one x such that fx equals y. That line is if is bijective, then for every y in y, because it is 1, there is, because it is onto, there is one x in x such that fx equals y. Because it is injective, you can have only one x. That's why it says, if f is bijective, then for every y in y, there is exactly one x such that fx equals y. In parentheses he says, there is at least one because of surjectivity and at most one because of injectivity. You cannot have more than one. This value of x is denoted by, I don't know whether you have seen it before, f minus 1 y, f inverse y. Because this is what is happening here, this is x, this is y, f goes from here to here, f inverse goes from coming back home. F inverse, x goes to y, y goes to x. One-to-one correspondence. I hope you got them. These are important for us. One-to-one function. So let me do it from this one. There is one good question here. When is the third question? When is the empty function injective, surjective, bijective? Think about it. Empty function, domain is empty, set. Range, anything. Can it be one-to-one by any chance? But when is the empty function injective, surjective, bijective? But maybe last part you can answer easily. It can be bijective when the range is also empty, no? Same set to same set. So it's kind of a not analysis problem, but images and inverse images. Okay. Any questions so far? I guess I'm not going that fast. Kuta, up to now you are clear.
But the last part I didn't understand, sir.
You didn't understand last para?
If inverse.
No, because if f is 1 to 1, suppose a function f is 1 to 1 and f is 1 to both. So what will happen is, suppose you take y here. Because it is 1 to, there is one x here such that fx equals y. Because of that, f is 1 to. But because f is 1 to 1, you cannot have another x such that fx equals y. So there is exactly one x such that fx equals y. That's what over there I said. Right? That is it. 100% clear? In pure maths, whatever we know must be 100% clear. That is the difference between other subjects and that's 3 plus 5 is 8, no? It is not 7.9. It is like that. All say, okay, inverse images and inverse images. Let's see here what's it. We know that the function fx2y from a set x to a set y can take individual elements x to elements fx in y. You have simple x in capital X, f takes x to fx belongs to capital Y. Functions can also take subsets in x to subsets in y. If you this way is better than the other this, yes, no.
Yeah, it's faster.
Fast. Yes. Okay, here you have x, here you have y. We have to make it faster than today. Yeah, but so far you are catching the definitions are etc. So that's why I'm distributing. If there is f, you take x to fx on this side. Similarly, if you take a set here, this set, it has so many x's, no? All the x's are going to come set here. So, if it is A, this is f of A. Every element x goes to fx. This one is, say, x1 goes to fx1. Every element in capital A has an image in this set. So that is called f of A. That's what the definition here is, I guess. Images of sets. If f x to y is a function from x to y and s is a set in x. S is a subset of x. We define fs to be the set. He has this double dots before the equal sign. Fx belongs to S. Image of the set S. So you have taken images of every element of the set S. That's what he has done. According to the over there, this is S. You take the images of elements in X. It's a collection of all of them. All of them. So this is Fs. Sometimes Fs can be a single thing. It can have one. It will never be empty. If S is non-empty, then Fs is not empty. So now what? This set is a subset of Y and is sometimes called the image of S. It is the image of S. Under the map F, we sometimes call Fs the forward image. You are going forward? Forward image of S to distinguish it from the concept of the inverse image of F inverse S of S. පුතා මම නවත්තනවා දැන්. අර ඒක ගේන්න නේ. පොඩ්ඩක්